Hello there, welcome to Ethio Hahu tutorial. I'm Getacho, and today we are going to see about oscillation. An oscillation is a back and forth motion along the same path, or a to and fro motion along the same path. An oscillation is said to be periodic if it repeats itself at a regular interval of time. Let's consider the system. This particle of mass m tied at the end of this string and moves back and forth along this path. This motion is a to and fro motion or a back and forth motion because this ball is pulled to this side and then released. When this ball is released from this point, it moves towards its equilibrium position and passes the lowest point of motion and reaches this point. And when it reaches this point, again, it comes back to this point and then back to this point. By this, it performs back and forth motion or a to and fro motion along the same path. This point x is equal to 0 is the lowest point of oscillation or the equilibrium position. And this is the maximum amplitude of oscillation. The particle oscillates with this amplitude. As it moves from the equilibrium position to this point, the amplitude increases, and as it moves towards the equilibrium position, the amplitude decreases. Therefore, when it moves from point A to B, the amplitude increases, and when it moves from B to A, the amplitude decreases. Similarly, when this particle moves from A, say, to C, the amplitude increases, and from C to A, the amplitude decreases. Therefore, the amplitude of oscillation is A, and the speed of this particle as it passes the lowest point of oscillation is maximum. However, this amplitude of oscillation decays in time. Why? Because the energy of oscillation gets smaller and smaller. Energy is directly proportional to amplitude square. Because when the amplitude increases, the energy increases and vice versa. As the particle moves from A to B, the amplitude increases, so its energy increases. As it moves from this point to this point, the amplitude decreases and the gravitational potential energy decreases. Therefore, as it moves from the lowest point to the highest point, the amplitude increases and its gravitational potential energy increases, whereas its kinetic energy gets smaller and smaller. As the particle moves from A to B, 1, the amplitude increases, meaning gravitational potential energy increases, whereas the speed decreases. The speed of the particle as it moves from A to B decreases, meaning that its kinetic energy becomes smaller and smaller. When it reaches point B, the kinetic energy is 0 and the gravitational potential energy is maximum. As it moves from B to A, its gravitational potential energy decreases, its kinetic energy increases, and at point A, gravitational potential energy is 0, whereas kinetic energy is maximum. An oscillation can be classified as damped oscillation, undamped oscillation, and forced oscillation. In case of undamped oscillation, the amplitude of oscillation remains the same. Amplitude remains same. For the case of damped oscillation, the amplitude decays with time. In this case, amplitude decays in time. Why? Because of the dissipative force, the energy of oscillation decays, so its amplitude gets smaller and smaller. The third type of oscillation, forced oscillation. The name forced indicates that we can apply external force for compensating the decreasing energy. As this oscillation takes place, the amplitude of oscillation, as I've said, gets smaller and smaller. To compensate this decreasing amplitude of oscillation or decreasing energy, we continuously push this system so as to maintain the amplitude of oscillation constant, and such kind of oscillation is said to be forced oscillation. Therefore, in general, an oscillation can be undamped oscillation, damped oscillation, and forced oscillation. Undamped oscillation is an oscillation with same amplitude. Damped oscillation is an oscillation with decaying amplitude. Forced oscillation is an oscillation with constant amplitude, but in the applications of external force. Having seen this, let's go to Hooke's law. Consider a mass m that moves in one dimension on a frictionless horizontal surface as shown below. This is mass spring system. The force constant of the spring is K, and let's apply an external force F to this block. What will happen to the spring? The spring will stretch by an amount X. This is the stretch of the spring by applying this external force. Or we can compress the spring by applying external force. While compressing the spring compressed by an amount X. In both cases, the external force is directly proportional to X. As we increase the magnitude of the external force, the stretch will increase or the compression will increase. And as the external force decreases, the extension will decrease. Therefore, the external force is directly proportional to the stretch of the spring or the compression of the spring. The external force is equal to K times X, and this is the external force applied to this spring. But as we pull the block to the right by an amount X and remove the force, the block will move to its equilibrium position. Why? Because of the presence of the restoring force. Therefore, the restoring force R is also proportional to X, but in the opposite direction. When the block moves to the right, the restoring force is to the left. Restoring force or an elastic restoring force is a force that restores or moves a system displaced from its equilibrium position towards the equilibrium position. And this restoring force is minus K times X, where K is the force constant of the spring. And this is known as Hooke's law, because the restoring force is directly proportional to the displacement of the spring or the stretch of the spring or the compression of the spring, and always directed towards the equilibrium position. In this case, the restoring force is to the left, whereas in this case, the restoring force is to the right, because the restoring force acts on this block to move the block to its equilibrium position. And from Newton's second law of motion, in the absence of external force, the net force acting on this block is equal to restoring force, which is equal to mass times acceleration. This is in the absence of external force. If the external force is removed, the only net force acting on this block is the restoring force. And this is equal to acceleration is equal to restoring force. Restoring force is minus K times X divided by M. And here again, the acceleration of this block is directly proportional to X and directed towards the equilibrium position. Both the restoring force and the acceleration of the block are directed towards the equilibrium position. As I have said, both the restoring force and the acceleration of the oscillating particle are always directed toward the center of the oscillatory path. There are parameters that can characterize an oscillation. One is period. Period is the time for one complete oscillation or revolution. Second, frequency. Frequency is the number of complete oscillation or revolution per unit time. And frequency is also written as 1 over period, where the unit of period is second, whereas the unit of frequency is hertz or per second. Amplitude is the maximum displacement of the oscillating system. Having seen this, let's go to elastic potential energy associated with a spring. Again, consider a mass spring system with force constant K. And let's apply an external force to this block. What will happen to the block? The block will move by an amount X. Therefore, how much work is done by this external force to stretch the spring. We know that work done is defined by dot product between force vector and displacement vector. But work done is equal to dot product between force and displacement is used only if F is constant. If F is not constant, we use the area under force versus displacement graph and the displacement axis. If we compress the spring by an amount x, again, how much work is done by this? Therefore, the question is how much work is done by the external force to stretch the spring by an amount x or to compress the spring by an amount x. Since this external force is given by k times x and variable, we need to draw first force versus displacement graph. Force versus displacement graph. This is the displacement axis and this is the external force axis. This is 0, this is x. The force increases linearly with position. When x is equal to x, the force is k times x. And the area under this curve is equal to work done. In general, this area method is used for constant force as well as for variable force. And this work done is the same as 1 over 2 times base times height. But 1 over 2 times our base is x times our height is k times x. This is equal to 1 over 2 k times x square. Therefore, work done by the external force is equal to half times k x square. And this is equal to half k x square minus half k 0 square. We can add 0 or subtract 0. 0 is additive identity. Now define elastic potential energy by half times k x square. Therefore, work done by the external force is equal to final elastic potential energy minus initial elastic potential energy. This is equal to change in elastic potential energy. Therefore, work done by the external force is equal to an increase in elastic potential energy. The amount of external work done is stored in the form of increase in elastic potential energy of this system. If this block moves at constant velocity, the net force acting on the block is 0. Assuming that the block moves with constant velocity, the magnitude of the external force is equal to the magnitude of the restoring force. Assuming that the block moves with constant velocity, that means V is equal to constant, means acceleration is equal to 0. Acceleration is equal to 0 means net force acting on the block is equal to 0. But from work energy theorem, work done by the net force is equal to change in translational kinetic energy. Work done by the net force means work done by the external force plus work done by the restoring force is equal to change in translational kinetic energy. Since V is constant, change in translational kinetic energy is 0 because translational kinetic energy is 1 over 2 m times V square. And since V is constant, final kinetic energy and initial kinetic energy are the same and change in translational kinetic energy is 0. This goes to 0. Therefore, work done by the external force plus work done by the restoring force is equal to 0. This implies work done by the restoring force is equal to minus of work done by the external force. We have found that work done by the external force is equal to change in elastic potential energy. This implies work done by the restoring force is equal to minus of change in elastic potential energy. This is work done by a restoring force. Therefore, this one is work done by force against the restoring force. and this is work done by the restoring force. If we sum up all these energies, total work done is 0. That means the change in translational kinetic energy is 0. Net work done by the net force is 0. In general, the restoring force is given by minus k times x. The acceleration of the block is minus k over m times x, and this is actually position dependent. This is also position dependent. Elastic potential energy is equal to half times k times x squared. When x is equal to 0, elastic potential energy is 0. When x is equal to amplitude, elastic potential energy is maximum, and half times k times a squared. Therefore, elastic potential energy depends upon the stretch or the compression of the spring. This is all about today. Next time, we'll see simple harmonic motion. Until then, have a nice time.